Okay, we're going to look at isotopes. So if you look at your periodic table, you can see, for example, we've got, let's say, argon here. We've got 40, 18. And we've said that this is the atomic number. And this is the mass number. Now, to be strict, this we should really say in the periodic table, it isn't strictly speaking the mass number. It is something called the relative atomic mass. And we'll see what that means in a minute. But we can see, right, if you wanted to work out the number of protons for argon, the number of protons, well, the atomic number is 18, so it's going to be 18 protons. And the number of neutrons, we would say 40 minus 18, which is 22. So far, so good. But you may notice there, if you look at chlorine, so look at chlorine there, and it's got this relative atomic mass number of 35.5. Well, does that mean that, you might think, so we've got, with chlorine, you might think you have got 17 protons and 35.5 minus 17, which is 18.5 neutrons. Well, you can't have half a neutron. It's impossible. You can't split a neutron up. So what's going on there? Well, relative atomic mass is taking into account that they are two versions of chlorine. And the two versions of chlorine are 3717 and 3517 chlorine. Now, these two different versions are called isotopes. Let's see the difference and the similarities between them. Well, look at the number of protons. This one here has got 17 protons, and it has got 37 minus 17, that's got 20 neutrons. Whereas this one here, the 35, has got, again, it's got 17 protons, but the number of neutrons got two less, it's got 18. So we can see isotopes, a little definition here. We've got they're always asking this question. Say, same number of protons, different number of neutrons. Now, it's important to realize that if they've got the same number of protons, then they're also going to have the same number of electrons. So that means they've got the same arrangement of electrons. So that means they are going to be chemically identical. So there's absolutely no difference in chemistry between these two different versions of chlorine, 3517 and the 3717. They're the same. One has got more neutrons in its nucleus than the other. That's the only difference. Now, why do we use this number 35.5? Well, you might think that is an average, okay? But you could see, well, the average of 35 and 37 is not 35.5, it's 36, isn't it? And the reason for that is because, and we in a later video we'll show how to work this out, chlorine is actually 75% of naturally occurring chlorine is the lighter version, the 35, and only 25% of it is the heavy version, 3717. So if you take into account the abundances, then you come up with a figure of 35.5, and that is what's called the relative atomic mass. Okay, right, let's just have a look at a couple of other things there then. So I just rub this out. Right, so you can see, let's have a look at copper. Here we've got copper, and you can see that's also got a fractional one. And copper, like chlorine, exists as two. There's one that's 63, and there's one that's 65. So again, they've both got 29 protons, different numbers of neutrons, and the average value is 63.5, and that must tell you that tells you that you've got more of this one naturally occurring. You've got 75% of that one and only 25% of the other. We also have a quick look here at bromine. Bromine, now it looks okay, it's got 80, but in actual fact bromine is made up of, none of them have a mass number of 80. It's all 79. Half of it is that, sorry, bromine, and the other half of it is that one. So an average value there, just simply add the two numbers together, divide by 2. That's an easy one to work out. The average value is 80. If you look at some more accurate versions of the periodic table, you might see, for example, lithium. In our version, we'll have lithium as has got a relative atomic mass of 7, whereas if you look at more accurate versions, there's 6.9. And that tells you there's two versions of lithium. There's one that weighs 6 and one that weighs 7. And the one that weighs 7 is obviously more abundant because the average value is 6.9. Okay. Right, so let's have a look if you can still look at some other isotopes there. Then, so what I've got here is periodic table, and I've drawn some elements on the right here. So let's have a look at this one. Now, I've given it the symbol alpha, so you can't tell what the element is. Which element would it be? Well, you might think, oh, it's this one here. It is sulfur because it's got a mass number of 32, but that's not important for what determines an element. What makes an element different to another element is not the number of the mass number, it is the number of protons. Okay, and the number of protons in this thing we've got here is 15. So you can see what we've actually got is we've got phosphorus. Well, how come this one I've called alpha there, so I'm going to change to phosphorus. That version of phosphorus has got a mass number of 32, so it's got 17 neutrons, and the one in our periodic table there has only got 16. That is actually a radioactive version of phosphorus, which doesn't occur naturally, but it's made in nuclear reactors and things, but it does exist, but it doesn't occur naturally. So that's another version of another isotope of phosphorus. Let's have a look at the next one down here, this 13,6 beta. Well, we're looking for an element which has got an atomic number of 6, which is of course carbon. So that is carbon. Is it the normal version of carbon? No, it's got an extra proton. It's got a mass number of 13. That behave in exactly the same way as normal carbon, just a tiny bit heavier. And that's I think it's 1% of all carbon atoms is naturally occurring is carbon with a mass number of 13, but they don't work out an average value because it's 12 is good enough to 1 decimal place. So that's why it just says 12 in your table there. Now these two are quite interesting. You might see they have both got atomic number of 1. So that means they are both hydrogen, but they're not the normal version of hydrogen in our periodic table, because of course that, the one we've got there, is 1 hydrogen. So right, this one has actually got 2 neutrons in the nucleus. That's a radioactive form of hydrogen. It's not found naturally, but it occurs in nuclear reactors and things like that. This one here, that has got 1 proton and 1 neutron. That one does exist naturally, and I think it's about 1 in 100 hydrogen atoms is this heavy version of hydrogen. Just a couple more here now. So we've got, right, what have we got there? That one, well, I put that one in because it's similar to that. They both have got a mass number of 32, but they've got a different atomic number. This one's 16, so this one is actually sulfur. See sulfur there, and that is the normal version of sulfur because it weighs 32. That's just normal sulfur. This one here, atomic number of 8, so it's going to be oxygen. Is it the normal version of oxygen? No, oxygen is usually 16. This is a naturally occurring but very, very rare isotope of oxygen, but it does exist. Right, this one here, 25, 12. Okay, so atomic number 12, well, that's going to be magnesium. Is it the normal version of magnesium? No, most magnesium is 24. That's naturally occurring. A very small amount of it occurs naturally. And in some versions of the periodic table, you'll see that the relative atomic mass of magnesium is given the value 24.1. Okay, but 24 is good enough for GCSE. But there is naturally occurring a little bit of 25, which makes the average value 24.1. So just to summarize there, just so you don't get mixed up, there's two differences. There's the mass number, and that's of a nucleus, really, just one nucleus, and that's equal to the number of protons plus the number of neutrons. And then we have something called the relative atomic mass. Let's say e.g. we've got 35.5 for chlorine, and that is the mass of an average atom. Of course, there's no such thing as an average atom. No atoms are average, are they? They're either 35 or 37, but this is taking into account the different amounts of the two isotopes, and you work out the average value. And then just finally to say, don't forget, isotopes of the same element have identical chemistry. Identical chemistry. They behave in exactly the same way. So in the next video, we'll see how to work out this relative atomic mass given the different abundances of different isotopes.